Hi there. Today I'm going to go through the reduction of order method proof with you. Last video I showed you an equation that looked something like this, and I've gotten questions as to how I got this equation in the first place since I didn't give a formal name for it. Well, I can show you now how the proof to get to this equation. The first step of this proof is knowing that y2 is equal to y1 v at t. We have to assume this, right? That we have to assume that there exists a second solution in the form of y2 equaling y1 v at t for some differentiable function v at t. And we also need a second order homogeneous linear differential equation. It's homogeneous because of 0, right? It wouldn't be homogeneous if this was some like f at x. Okay, so the first step that we're going to take is we're going to compute the Wronski of this homogeneous equation. It might not make any sense right now, but it will in the end. So, there are two ways to compute it, and we're going to do it both ways. Let's do the first way, which is by finding the determinant, which everyone should know how to do, right? I'm going to skip a step here. This is actually y2, but since we already assumed y2 is equal to y1 v at t, I just plugged it right in. I hope nobody minds. Here we go. And of course the second line of the Wronskian is always just the first derivative of the top guy, right? Now, we're gonna expand. Well, by expand I really just mean solve it. It's a little long, this step. Of course, you're not going to be doing this every time you do a question, so don't worry about that. This is just to prove that the equation works. So, what do you get from this? You get y1 squared v prime at t. I'm going to keep that in the back of your head because we're going to use it later. Now, the second way to derive the Wronski of a second order linear differentiable homogeneous equation is by using Abel's theorem. Yeah, that's how you spell it. Okay. So how do we find it? Well, we go like this. I'm not going to prove Abel's theorem in this video because it would take a lot of time, and I don't think you need to look at it really. It's pretty easy. Now, this c is a constant, and this c is not equal to 0, because if the Wronski was equal to 0, this would not be linear independent in y1 and y2, and we need linear independence in y1 and y2, right? So, let's continue. We've got these two brilliant equations, and what we're going to do is we're actually going to equate this guy and this guy, and we're going to get this. y1 squared v prime at t is equal to c, which is a constant, e to the negative integral p at t dt. Now, hopefully you can start to see the equation take form, because if I just divide by y1 squared, what I'm going to get is my magical, very useful, fast and easy equation to solve difficult questions, right? Right. Now, we got to deal with the c. I just make the c 1 because this c is just like some arbitrary thingamabobber. You're never really gonna need it. I know it's weird if I just shrug it off. You're also gonna be like, why are you doing that? And I'm just gonna tell you, just do it, just trust me. It's probably magic, you know? Anyways, yeah, this is that equation that I used. So let's finish it off by stating that the general solution is also still going to be y is equal to c1 y1 plus c2 y2, right? Therefore, if this is true, y is equal to c1 y1 plus c2 y1 v at t, right? Yep. So that's how I got to the equation, and this is the proof for it. I hope that you found this video helpful, and if you have any questions or concerns about this method or any other questions in general, please feel free to ask in the comments below. Thank you.